In this video, we're going to discuss one of the problem areas I had when I first took calculus, and it was tough for me. I'm not going to lie. It you know at the time I thought related rates was easier. So some people may cruise through this, others you may struggle like me. And so I decided I'm going to include quite a few of these videos so that y'all have at least a lot of examples to work through and to try to help you understand how to do this. And you can have whole classes on this. I mean, it is not an easy thing. Uh, so let's start right out. We're talking about optimization. Optimization is typically one of those things where you have a set amount of something, but you want another attribute to be a maximum or a minimum. So for example, I'm looking for two numbers whose sum is s. So it has to have a sum of some sort. And the product is a maximum. So I want to optimize my two numbers, or the relationship between my two numbers, so that the product of the two is a maximum. Okay, and so this sounds like, oh, well, this isn't, why would I ever use this? Well, if you're a landscaper and you only have X amount of fencing, then you can figure out, well, what's the best shape, essentially? What is the best shape that I can put this in to maximize my area of confinement? All right, so let's go through all these and you can kind of see how it breaks down. So number one, make a list of all the variables and values of known variables. Well, we don't have any known variables, and so I'm going to simply choose the two numbers. So x, this is my first number. Y is my second number. Okay, so now that's fine. All right, now number two, determine the equations needed to be optimized according to the variables in step one. Okay, so I want to optimize my product. So I want to optimize x, y. This is equal to my product. I'm going to call it P. Okay, so now most of the time you will need to have at least one supporting equation that relates the variables in a slightly different way. For examples, if you're optimizing volume, use the surface area as a supporting equation. In this case, it kind of leads us. It says the sum is S. Okay, so we're going to go ahead and work with the sum. So now we know that x plus y must equal s. We don't know what s might be. And if I'm a landscaper and I'm doing this, I don't know necessarily how much fencing the person's going to allow me to buy. But I know that it's some value. So I'm just going to call it s as that value. Now, part 4, determine a viable domain. Well, since this is it's a maximizing the product's probably going to want to be positive. And right now, it doesn't say this, but it just says find two numbers. In the original problem, it was find two positive numbers. Okay, I probably should have put that in there. So x is greater than 0, and this is greater than 0, and this is greater than 0. It just doesn't make a whole lot of sense to, now if you are minimizing the sum and maximizing the product, then we want to look at both negative numbers. But since we want to maximize the product and we're not really told what the numbers are, let's just stick with positives. It's a little easier to do. Number 5, find the derivative, set it to 0, and solve. Now, we're always working according to the optimizing equation, and that's always the one that they give you to say we want to have the maximum or minimum. Which means if we have p is equal to xy, I would like to find the derivative of p. Now, we haven't worked with more than one variable, and so the idea here is use this secondary equation to rewrite one of the variables. I'm going to go ahead and I'm going to choose to rewrite x, and so, or to rewrite y. And so if x plus y is equal to s, then that means that x is equal to s minus y, or I should say, well, it doesn't matter. Okay. So now this doesn't look like it's helped, but I already know what s is, or at least that's the assumption. And so I'm going to say, all right, well, let's rewrite it. P is equal to, and wherever I see an x, I'm going to put s minus y. S minus y times y. And so I'm going to go ahead and expand this. sy minus y squared. So if we were to look at this, we have a -1 out front of the y squared, and that's the dominating degree. And so this thing's going to look like an upside down parabola, which is good because we're looking for maximum. So all we do is we take the derivative of our equation that we want to maximize according to the variable. S is not a variable, it is a constant. And now when we do this, we have s minus 2y. Now set that equal to 0 and solve. Okay, so we set that equals 0. Well, if we do that, then s minus 2y is equal to 0, which means that s is equal to 2y, which means that y is equal to 1/2 s. Okay, so if y equals 1/2 s, then we can take that and plug that into the secondary equation and find x. So we know from above here, we know that x is equal to s minus y, but y is 1/2 s. So x is equal to s minus 1/2 s, which is 1/2 s. Okay, so at the end of all of this, we have x is equal to 1/2 s, y is equal to 1/2 s, so x equals y. Okay, these are the values they're looking for. But the more important thing is the two numbers must be the same. Now, if you look, there's really not a big difference between this problem and the problem for maximizing the area of a rectangle. If you say you want to enclose a rectangular area, well, my perimeter is going to be 2x plus 2y, but that doesn't change the problem too much. You simply still go through the whole process. The only difference is you just have something more to cancel out when you take the derivative. And so you'd have a certain perimeter, and then you want to maximize the area. And look, it's x equals y, it's a square. That's it. That's all it has to be. Sometimes they might give you a number for product or for the sum, but that's fine. No big deal. Just follow the same steps.